Today we're going to be talking about how we characterize our data, how we talk about it. There's some figures of merit that we use to describe our data, like normality tests and so on, and skewness, and we'll talk about different distributions of data. So that's the main thing today, is just other statistical tests and terms. And here's the summary, the graphical summary that we get from Minitab on the trainee data that we looked at. And so this is a histogram. Are you familiar with histograms? Have you seen them before? Nod your head. Yes, okay. I've seen a few people nod. And what you're doing here is you've got, let's look at some of the histogram terms. Okay, these blocks here are called bins. Okay, they're kind of like buckets or bins, right? British, they call them bins, we call them cans or buckets. And this axis is called frequency, meaning how many times in that bucket do you have a data point. Okay, now we had 10 data points, which is not a lot, right? It's just a sample, it's not a population. And so this bin, if we look at this, we got 1, 2, how many do you think are in this bin, these bins? 1, 2, 3. So it looks like 3 in that bin. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have all 10 data points that we can account for. But you can see that if it falls between these two limits here, that's not saying those 3 data points are exactly the same. It says they fit in the limit of that bin. And so how you pick your bin width will change the picture of your histogram. Okay. So let's say if we just had 2 bins, so we just made our bin width here, and let's say here, we'd have 6, 7, 8. So we'd have a huge stick going up to 8, and then this stick would only go up to 2. And so that's what our histogram would look like. It'd be 2 blocks, one with 8, one with 2. And it doesn't really give us much information, and so we would shrink that bin width and make it a little bit more look like a distribution. If it's perfect, let's say we did 1,000 measurements and everything was ideally, like we had the mean value and then only like small random variations, it would look like this blue curve. This blue curve is a normal distribution. Normal distribution. And that's also a Gaussian curve. Okay. So this Anderson-Darling normality test is giving us the p-value here for our data and saying what's the probability that it's normally distributed. 17 or 19%, 19.6%. So we only have 10 data points, so it's saying it's possible that this is normally distributed, and it's just kind of just a test to see if your data is skewed or has kurtosis. If it's normally distributed, it's more symmetric. Okay. Now, if you're looking at these statistics terms, let's say you come across these tests, you can always go to the stat guide in Minitab. You can also look at the help in Excel. Both of those menus are pretty good. Excel has been around for, let's see, I started using it in my graduate work in '93. So it's been around a while in terms of, and so at first the help menu was useless. You would ask it how to open a file, and it would say go to file open. It was really very basic help, but now they've got a lot more on the functions. They got little sample examples and everything like that. So I don't know if you've ever hit F1 whenever you're in Excel, but that'll bring up the help menu. And it's even better now with the gosh, what is Bing called there? Copilot, I think, or Cortana. Anyway, there's an AI now, and I'm telling you that the AI helpers on Bing and now on Google, they're really good. I mean, you can type out a really long question and it'll distill the information from the websites and give you a really good response. And and I wouldn't necessarily put that in a paper, but as far as trying to answer your question, they've answered a lot of my questions right away, and it's been great. So this is, again, you can't use a p-value unless you know the null hypothesis, right? And so this is the null hypothesis that the data follow a normal distribution. That's the Anderson-Darling normality test. That's the null hypothesis, and the p-value is the probability that that's true. Okay, and if it's less than 0.05, we would reject the null hypothesis. Ours was 19.6, so we're going to say, yeah, as far as we fail to reject the hypothesis that our data is normally distributed. You can also compute it for other tests, other distributions as well, meaning you could use it to determine if something was a Poisson distribution or if something was a Weibull distribution. But we really only focus on the normal distribution in statistics. Okay, and it's just included by default for the mini-tab. Now here's the forensic chemist. And our normality test is 0.017. So would we say that this data is normally distributed? So the null hypothesis is that the data is normally distributed. The probability that that's true is 0.017. So we would reject that null hypothesis, and we would say this data is not normally distributed. Is that a problem for our data set for the forensic chemist? I would say no, because we only have 10 measurements. We really don't know. If we can continue to collect data by this chemist, and we got up to, and we say 15 is the magic number that gives us a population, but really to determine if something is normally distributed, we would need many more. And so if you do this, if you have forensic chemist data from the whole year, and you have on this check sample that they keep doing just to sort of check on themselves, and you get 50 to 100 samples, maybe they do once a week and you get all 50. I would propose that, this data is going to fill out a little bit, and it's going to be more normally distributed around a mean, and that it's going to look like that. So I wouldn't make any big deal out of this as long as we have a small sample number. Okay, let's look at some of the other things on this graph. We get some nice statistical values out of this, the mean, okay? We get the standard deviation. We can calculate all these in Excel. In that homework assignment, you did all of that by hand. The beautiful thing about Minitab is, and other statistical packages, I just show this one because it's one I'm familiar with, is you have your data in a column and you just go up to stat, graphical summary, here's my data, go. It produces this. You don't have to type in any formulas. There's no equals average and select the range, and then equals standdev dot s in the range, and all of those little tedious things that you did. We're not doing them by hand with a calculator, but doing them in Excel is still classified as by hand because you're typing in the formulas. And in Minitab, you just have the data there, and you just analyze the data. You just graphical summary, there it is, and you get all of this result. Of course, the standard deviation squared. We have this is x bar, this is s, this is s squared. But then we get to these two terms, skewness and kurtosis, and we'll talk about those today. Then we have the quartiles, and these quartiles are shown here. This is the median, okay, and this is the lowest. Let's see, the first quartile, 13.1. So I'll say 25%. This is 50%. This is 75%. And this is 100%. So those quartiles are also the percentiles, but we mark those points where the 25th percentile is here, 50th percentile is the median, the 75th percentile is here, and then this is the maximum value. So that's this whole block right here. Then we have the confidence intervals for the mean, and that's shown here. So this is our average value. Now this is a different scale, so don't compare this to the chart above, right? This is just showing you a different scale. So this is the mean, X bar, and then this is plus 1.96. Well, actually it's that, this is a good opportunity to show the sample confidence interval. Okay. So this range right here uses this formula, plus or minus on both sides, right? T S over the square root of n. And this T depends upon the degrees of freedom, right? It's that T inverse Excel function. So for a sample, when you have for n less than 15, you need to use this T inverse function to calculate your confidence intervals. Okay. And then this ratio right here approaches z as n goes to infinity, right? So when we have a large number of data, then we can use z and not worry about the degrees of freedom and the number of data points and so on. So if we have 15 or more data points, we can just use z. If we do a linear regression where we have lots of data points in our calibration curve, then we can use z for that plus or minus confidence interval, 95% confidence interval. So the uncertainties in the slope, the uncertainties in the intercept, we can use z from an ANOVA output. Now there's also the median here, plus or minus, and I do not know, I've never pulled the thread because I've never needed to, but here it produces the confidence intervals on the median, which that's math I've never seen. It's kind of interesting. And it also tells us the standard deviation and gives us confidence intervals on the standard deviation, which I've never seen that math either. So these two right here are nice, but I don't know how they're calculated. So if you're just really, if that bothers you, great, go for it. Tell me about it, when you figure it out. Okay, so that's the graphical summary. And it's a very nice thing. This is the kind of reason why you would want to, if you're doing this as your job, want to get a statistical package like Minitab. Even though we teach you Excel, we try to teach you the what's under the hood of a lot of these things. But in day-to-day operations, it's much better to just have your data menu, click, go, and you get all your information. Okay, now let's look at some of these other terms. This is kurtosis. And this is telling us that our kurtosis value is 3. Is that good? Is that bad? What is this thing telling us? Okay. So let's look at the Minitab stat guide. Okay. Kurtosis is the degree to which the data set is peaked. Okay. Data that follow a normal distribution perfectly, okay, would have a kurtosis value of 0. So that's normal data, kurtosis would be 0. It can be negative, it can be positive. So sharply peaked data has a positive kurtosis value. Now, and then flat peaked data would have a negative kurtosis value. So when would these be alarming? Well, let's say we had an enormous amount of runs on our trainee and on our forensic chemist, and they both had pretty good standard deviations, but they were off a little bit. So this has a normal distribution like this, okay, and that's one of our analysts, and the other one has a distribution like this. And you see how I might have 2 peaks under that flat topped curve or histogram. So this is detecting unresolved bias, so that these analysts are giving different results on average, and they're similar precision, and they're just not resolved. And so we have a pretty steep curve because this analyst is precise. But then as soon as this one starts to go down, this one starts to come up. And then it has a steep curve because it's precise. And so this is detecting unresolved differences in our means. Okay. So this might be like mean number 1 and mean number 2. And this is detecting something's weird about our data. That's really all it is. It's just like, it's something strange about our data. It has a kurtosis value that's very negative. So I might have two distributions in here. And I need to look at the information. Let's say we had this data and we didn't know that there were 2 people involved. Okay. We're like, wait, we've got really flat topped data. We've got something going on. We pull the thread and we're like, oh, we see in the data table, there's like analyst A, analyst B, analyst B, analyst B, analyst A. And then we can split those apart and we see, okay, analyst A is a little bit high, analyst B is a little bit low. We would not have known to look for that if we didn't know about this kurtosis value. Okay, what about this one? What kind of scenario would give us this shape of a curve if we had 2 analysts? Or maybe two baggy seizures or something. We had two things in our data set that we didn't really piece out. We just looked at the data and we got this strange distribution with sharply peaked data. What? The same what? You know it. You know the word. What's the same about them? The mean. Very good. Yeah, so they have the same mean. They're both centered, right? But what's different about them? Someone else. So this is 2 distributions that have the same mean, but what's different about them?
Wouldn't one be mostly lower numbers that average higher than one's higher numbers that average lower?
You're onto something. So remember, these are not the measurements they're making. This is the frequency at which they got various measurements. So the measurements, that's great to point that out. So let's say this is milligrams of per pack or something like that of cocaine on the x-axis, and this is how many times their measurements fit in the bin, right? So they have the same mean, meaning that, you know, all of their packs that they measured had the same average milligrams of cocaine per pack. So they both agree on the mean. And they did the same number of measurements. And so the area under their curve should be the same. So what's different about the 2 distributions? The standard deviation. One person has a really wide standard deviation, and that's this peak right here. So this person has got like that. So they made the same number of measurements as the other person, but their scatter is spreading it out. That's why their bins are the same. They're really low numbers in each bin. And then the other person, very narrow standard deviation around the mean, and all of their numbers fit into 2 bins because they got the same answer so many times because they had a very precise measurement. And so their distribution looks like this. You see that? So they've got 2 different, so then we parse the data and we're like, oh my gosh, we had 2 analysts, or we had 2 packs. And one was well prepared with the same amount of cocaine in each pack. It was a very anal retentive drug dealer, you know. The other one was like all over the place. Okay. Or the analysts. One, you know, has really good technique and all their data is right online because the packs are all the same. And the other one is kind of all over the place in their technique. We don't really know. We would have to pull the thread to see that. But we do know that this positive kurtosis value told us there was something interesting about our data. And that it wasn't normally distributed. It might actually have 2 different distributions in there. Which one of these, let's see, if we determine those 2 distributions, what test would we use to test between these 2 distributions? Would see it, you know, if there's 2 different standard deviations, what test would we use to determine that statistically? The F test, very good. So F test. so we would, if we could pull that data apart and see the really narrow one and see the really broad one, we could say, well, is it a kurtosis value just because we don't have very many data points, which could happen. If we only had 10 data points, I wouldn't worry about this. But if we had 1,000 data points, I would say, somebody really got a really broad standard deviation. Somebody's got a really narrow one. Is it statistically significant? We do the F test and say, yeah, there's a 0.001 chance that they have the same standard deviation. And so we would wonder, what's going on with those two analysts or those two instruments, those two labs, or these different seizures. Over here, if we could get these two data, remember these had different means. So we had a mean there and a mean there. What test would we use here? Yeah, the t-test. If we could find those two distributions, it's giving us this negative kurtosis value. Okay, so you've probably heard of skewed data, but you probably have not heard of kurtosis. Okay, in fact, when I started teaching this course, that was new to me too. So I was looking, I was like, what is that? And so anyway, now we know. Okay, so then skewness. Okay, this is a 1.13. Is that good, bad? What are we looking at for skewness? And here's the forensic chemist. It's even more skewed, 1.34. And so this is a positive value, okay? And this is the high side. So this means it's skewed to high, skewed to the high numbers. So when it's positive, the tail, so it's kind of hard to see with our small number of data points, but it looks like this. Okay. And so this is, I don't know if you're Star Wars fans. Jabba the Hut. Okay. And his little hand, he's got the frog, the little. Okay. So where's this tail go? That's when we talk about the tail of the distribution. We know Jabba the Hut has that long tail, and the tail goes to the high side. So now you won't look at skewed data without seeing Jabba the Hut. So my work is done here. See you later. Okay. So here, positive is right skewed, but this is a bad way to think about it because right and left implies that we're plotting the data small to large going to the right. Okay. So we can say that if we're looking at the chart, it's skewed to the right, but you got to look to see if it's high or low numbers. So right skewed, I would say skewed high is skewed high to larger numbers, and negative skewness is skewed low to lower numbers. So the right and left, I mean, yeah, it fits with this diagram, right and left, but you need to look at the x-axis to see what data, how it's plotted. Is it high numbers to the right or high numbers to the left? And so skewed high and values. Yeah, low values. Okay, so this is, and you can see, you can see good old Jabba in there. Okay. So let's look at some examples. Salary data has positive skewness almost every time. And so here's the salary data for annual household income. This is a 2010 estimates. It's kind of old. So down here it says categories in $5,000 increments, with the exception of the last two groups. And so these last two groups, they bunch in a 50. Let's see, this is 200 to 249. So these were 5,000 up to here, and then it goes to 50,000. Okay, and then this last one is greater than 250K. Okay, so everybody that's greater than 250K goes up. Okay, and this is percent of households right here. So right away we could say, like, in 2010 their estimate was a little over 2% of households made 250K. Now this is households with maybe multiple earners. That's pretty decent money. But where's the median? This is the median. So the 50th percentile was around $50,000, $50,000 to $55,000. Okay. The mean. Let me see if that's right. Yeah, the average. Let's see. The average is probably around here, because these big numbers right here, these huge numbers right here, will pull this. The average is always pulled high above that median because of the higher numbers. Okay, they have such an influence on the median, that on the mean, they drag it high. And so whenever you're looking at salaries, and this is, you're about to search for jobs, right? Use median income, not average. Average is pulled high by the CEO or whatever. So if you're looking at a company or a state or a city, don't look at mean averages, look at median. Median is the 50th percentile. That's right in the middle. Okay. Now there's another one on here too. What's the highest peak called? Do y'all know what that is? Mode. Very good. All right. Get a sticker. Okay. I'll get you one later. Okay. So this is the mode. And that's the most probable. Right? Over 6% of households have that salary, and it's 15,000 to 20,000. That's depressing. But anyway, it's, that's the most probable, right? These are all probabilities, percent of households, and that's over 6%. None of the others are above 6%. So that mode is the one we would say is the most probable. But somewhere between the most probable and the 50% mark is something that you could expect going in. You would expect, hopefully. And you can see Jabba here. Which way is this skewed? Well, it says up at the top. It's positive skewness, right? Towards the high values. These aren't in your notes, but I added some new ones while I was looking at this. I was like, let's look at, since we're talking about income and you guys are graduating seniors, forensic scientists. Okay, this is from Zippia, career expert, updated to 2021. So salaries have changed a fair bit since 21. Inflation has gone up. Salaries lag inflation, unfortunately for everybody. So inflation bumps, but then there'll be a catch up. If inflation doesn't come down, there will be a catch up as those higher prices percolate through higher revenues, and then those higher revenues and the competition for the job market will cause salaries to creep up. The sad part is that buying power of your money is depressed while there's inflation before salaries catch up. But when salaries do catch up, your mental state will be thinking of those dollars as if they had the buying power today, but they have the buying power then. So buying power will catch up. It's depressed now, and you'll feel great. You're like, man, I'm making $100,000, say in 7-8 years. But you'll be thinking of $100,000 as you think of it now. But $100,000 then will be the $80,000 now, or the $60,000 now, right? And so, I'm not trying to depress you, but I'm just saying that but like my sister, she, like, when she got her job in 89, I think she graduated UT with a master's in accounting. I mean, she was like making enormous bucks. Okay, now this was 88, 89. She got $33,000. She was like, I'm in the big time. Yeah. So, again, have things changed? Yeah, things have changed. This is, more than twice that. Okay. So this is average salary. Now there's the different ranks, but you can see a slight skew to the data here. 90th percentile, here's the median, 10%. So 90th percentile, this bin is 112,000. They don't really give us the bin width here. They just kind of give us the median and the 90th and the 10th percentile. Okay. So just a reality check. This is not going to be your starting salary. This is the top 10% in the forensic scientists, in fact, you're probably, when you get your first job, you are like a total risk to the company. Who's going to have the errors? Who's going to have the mistakes? Who's going to hurt themselves? Who's going to break things? So don't be depressed if your offer is here at 45,000. Okay, that's maybe not what you're expecting, but look at the potential for growth. Okay, and so if you show up on work and you're not drunk and you're reliable and you don't break things and you're teachable, you're going to move up pretty quickly. So you're starting at the bottom because you're a risk to the whole operation, and then they got to train you, they got to invest in you, and then you'll start moving up. Okay. Here's some other chemist jobs. Here's an environmental chemist job. So it's a little bit more distributed. We have more bins, I guess. Low end 36, high end 110. This was from, it's on the next page. ZipRecruiter, I think. Yeah, ZipRecruiter. Here's chemist salary in Houston, also around 60,000. Again, that's median. So that's the 50th percentile. And 50-50 chance of being on the high or low end side, but if you look at the distribution, probably a little higher chance of being on the low end. Was that neat? Was that helpful? Okay. So if you have a trouble finding a job, you got a chemistry degree. There are thousands of jobs in chemistry. What I want to say though is even our folks that come out, that we had a downturn like 5 or 6 years ago, and job hunting was really tough. But even our scraping the bottom C students were getting jobs before the end of the summer. That wasn't happening on the other part of campus, right? Some of the other degrees. And when I was in a meeting and they were talking about how bad the job market was, and I was kind of keeping tabs on some of the folks that got out with the C-, average GPA, but they got their chemistry degree. They had some skills, right? They were getting jobs still, even in 6 months to 2 months, 6 years, goodness, 6. The word is weeks. 6 weeks. I went through all of them, didn't I? 6 weeks to 2 months is what I was trying to say. And so, but a couple of them they were a little worried. They had to go through what's called CHEMs. Now, in back in the 20s and 30s, early on, when the companies were growing really fast, they started these things called temp agencies, and they were mostly for typists, right? Come in and type up receipts and type up invoices and all of that, and it was temp work. We've got an annual report due. We need 3 more typists. They work for 2 months and then they're gone. It was called Kelly temps, and now Kelly's broadened, and they now have a scientific division. So it's Kelly Scientific, and it's temporary work. And sometimes the contracts are fairly long, like 18 months. So some company in Houston, refinery or whatever, has opening in their chemistry area because they've got a big push. For whatever reason, they need extra chemists at the bench, and they'll hire somebody on a temporary basis. The other side of things is it's a test drive. Remember what I was saying about you being a kind of a danger to a company, especially a chemical company. They want for them to bring you in and commit to training you and commit to giving you all your benefits and your retirement and all of that is a huge, huge lift for them and a huge commitment for them. So if given the option, they'll go through Kelly temps and they'll test drive employees for 18 months. And then a permanent job will open and you're an inside candidate for that job. So if you've done well in the 18-month trial period, then it's pretty high probability that you'll be brought into the company on a permanent basis. Then you get your full package of retirement benefits and all of that stuff. But you would be contracted to them for a short period of time through Kelly Scientific. So that's another option too. It's better to aim. I would say my personal preference would be aim for the permanent job. Okay. But don't be worried about if you need, if bills need to be paid, right? If you need to move, you need to get a job, and you still want to use your degree, that's a really good thing. Don't just go to the mall and start working at Dillard's again. Go find, Kelly Scientific or something similar. Pick a city that you want to live in, and then do that, and then you'll be able to prove yourself. You'll get hired on, and all of those people that got hired on through the temp agencies have now moved into permanent positions, and some of them have really blossomed. So it's been fantastic to see.
And some of these places, they would help with your education, I'm guessing, right?
Which places?
I'm saying like in jobs in general.
Yeah, okay, so jobs in general. So a lot of times folks want to go to grad school and all of that, and then it helps your salary and things like that in many cases. But if you want to go ahead and get into the workplace and get some experience, the bigger companies will sometimes help you pay for your master's or even some for a PhD. So that's another route for the higher degrees. Typically, those packages will require you to pay them back in times of service. So if you go to, like at Pantex, they had a great program. If they wanted you to move into a technical managerial role and they wanted you to have a PhD, they would send you off to get your PhD, and you had to pay them back 2 years for every year. So if it took you 4 years to get your PhD, you had a requirement to work 8 more years so they could get their investment back. Okay, but what a sweet deal, because they paid you something like 60% of your salary, and they paid for your tuition and all your books and fees. So you didn't pay for the degree, and you got paid while you were there 60% of your salary. So it was really, really good. And that means you didn't have to TA, you didn't have to hustle and do some side job or anything like that. You could focus on your studies, which meant also you probably got out sooner because you were able to do research and do your classwork, and you didn't have to have a side job. So if you could only do your classwork and your research, you'd make better progress, as you guys know, as many of you work. Unfortunately, age at death has negative skewness, right? Java's looking the other way now, darn it. Okay, sad, okay, because it's death. So his tail goes down. Now this bump down here would be like less than 1 year, so this is infant mortality, okay? That's going to drag the average down, okay? So the average would be here, so we would say mu. I don't know, has anybody ever seen a letter for the median? I don't know of a letter for the median, so I have to write the whole thing, median. And then these are the modes. Okay. And you can kind of see the differences in male and female here. That was like right here, Jeep plus beer. Okay. Right. And that's the insurance companies. They're like, all right, insuring a young male 25-year-old for driving a car. That's why the rates are higher. That is a clear statistical reason. So, anyway, there's not that much difference, but tell that to the 85-year-old who wants to live to 90, right? So overall, we make light of these small differences in years, but when you reach those years, you're like, yeah, I would like a few more years, or maybe you wouldn't. I don't know, but situations are different. But this is negative skew, and it goes to the lower values. Okay, now skewness, again, is just how symmetric the data is. So both of these crazy situations have a 0 skew because they're symmetric. Okay. So just lack of skewness doesn't imply normality. We would need to look at the kurtosis too. I don't know what the kurtosis would do with this because it's not really peaked. I mean, this is like a normal distribution, so that would be kurtosis 0. I don't know what kurtosis would give in this one. But we describe this one as bi-modal. So this is something you need to look for. Remember, the mode is this most probable here. And the most probable is going to be next to the next nearest neighbors, right? If there's another really high probability anywhere else, we would call it bimodal, or if there's 3 of them, trimodal data or multimodal data. So we have 2 modes here, bimodal. Yeah, 2 separate means, 2 separate deviations. Now, what on earth could happen here to give us this sharp cutoff, right? Why this abrupt cutoff? Well, sometimes the data is limited. Like if you were doing things in terms of minutes per day, right? 0 is one end, and you might have a lot of things that were real close to 0, and 24 hours converted to minutes would be the maximum, and you would hit that point and flip over to the next day. So that would be a sharp cutoff on that. So if this was something done daily, you would say, well, in one group of measurements, it's essentially 0 plus a little bit, and the other group is it's 24 hours plus a little bit or minus a little bit. Okay, so this would be examples where you have just natural limits to the data, so you get this sharp cutoff at the ends. So here is an example of a misleading mean and median. So if you have the data here, this mean and median may come out right here, and without looking at the data, the histogram or its distribution, you're going to assume incorrectly that this is a probable result. Let's see. The mean represents the distribution. So we must look at the distribution. That's my little eyeglasses. You look at the distribution to see if it's multimodal, if it's Gaussian or whatever, and that's why the Minitab does the histogram and shows the Gaussian blue curve on it, so that you can compare your histogram to a normal distribution, and it does the normality test. The normality test, if it's got a good probability and the null hypothesis is true, that it's normally distributed, then the mean can be assumed to represent the data. But if it's not normally distributed, you might say, let's look, let's gather more data points. Let's see if this mean is misleading. And so if you have multimodal data, this is bimodal. So you really want to look at, you've got 2 means, 2 medians. And so these are representative of the 2 distributions you have there. The overall mean and median is misleading because this is the probability of being at the overall mean, and it's less probable than any of the other individual numbers. Okay, lastly, this is something not, and I don't think I know I don't test on this. What I wanted to do here is just show you what we could do with the trainee and the forensic chemist data in terms of what's called a capability analysis. So every manufacturer, every process, and certainly in the crime lab, everything has a specification limit where you make a decision. What's the decision? This is a good part or a defect. In the forensics lab, this is worthy of a criminal charge or not. Right? The data is on a continuum, but there's some point where you make a decision. That's greater than 2 ounces of marijuana or not, right? And that ups the charge from whatever. I forget the law, but anyway, for a while there was, personal use or a large amount, and there's some cutoff. Well, that's a specification limit. Okay, and in this case, let's just make one up for our forensic chemist and trainee. We had that 13. I think it was 13.1 was the accepted value for the cocaine that they were each given. And let's say that our charge, our specification value was, if it's below 10, it's just contamination. If it's above 10, it's a criminal charge. So 10% would be our specification limit. So we've given each one a sample that's clearly above 10. How many times would they have a false negative, right? So every sample that they're analyzing should receive a criminal charge. It's 13. How many times would they incorrectly get it below 10? You see the question? That's a false negative. They're all positive. We know that because we built them. And so if they come out with something less than 10, that's an incorrect result. That's a defect. Just like if I was trying to make meter sticks and one came out, it was half a meter. That's a defect, right? And so this is, again, in the statistical package, you can put in your data, do a capability analysis on the cutoff of 10%. That's really all you have to tell it, and it'll do this. So it does this is the trainee. You see the histogram, you see the distribution, and I'm not going to explain everything on here, but this is the main thing I want to point out. The parts per million below the lower specification limit, LSL, that's lower spec. Lower specification limit. And again, in our fictitious scenario, if it was below that, there wouldn't be a criminal charge, or it'd be a lesser charge. But above that, then it would be a charge. And so this is some specification that we have in our analysis. And this is saying that the trainee with their standard deviation would come in at 972 parts per million. So 972 times out of 1 million analyses. That's not too bad, but it could be way better. Okay. So that's that would be 0.0009. Okay. So that's 900 out of a million, right? So this is the decimal thing. Or if we do this in percentages, I would move the decimal place 2 to the right. It would be 0.09%. Or it would say out of 10,000 analyses, which is a lot, 10,000. Out of 10,000 analyses, they would have 9 false negatives. Okay, that's not too good, really. Because what if this is, again, we're running a drug testing lab, and we're doing all of the NCAA athletes every year. We're going to have some people get through with drugs, and we've said they're clear. Okay, and so that's something that to consider. You might do 10,000 analyses a year if you have auto samplers and ELISA techniques and all of those things. Multi-channel plates. I mean, there's multi-channel plates that have like over 1,000 wells in them, and if you're uncertainty, you're going to have 9 errors in every 10 plates. So that's not good. So again, we want to shrink that standard deviation. Look at the forensic chemist. Look how narrow their uncertainty is compared to the lower specification limit. 13 is not that much higher than 10, but if you have a narrow standard deviation, you're a long way away from the lower specification limit. And so this is saying that the forensic chemist can even get down here to 11. Like they could tell the difference between 11 and 10 and still maintain a decent capability for determining when something's positive or not. Okay. And so you might hear this quality program called 6 Sigma. Ideally, we would want to be here. This is our mean and this is our standard deviation. That's sigma. We would want to be 1, 2, 3, 4, 5, 6 away from our lower standard deviation, our lower specification limit. So this forensic chemist is easily meeting the 6 sigma limit. If you are 6 sigmas away, and then they say long-term variation knocks a couple of those off, so it's like 4 sigmas away, then you're going to have 3 defects per million opportunities. So then it would be after every million samples, you've got 3 false negatives. If you're 4 sigmas away from the spec limit 10. So you could set your administrative limit to 12, roughly, and you would be assured that the forensic chemist would never be give a false negative if the values were 12 or higher, 3 times out of a million. So that would be operating at a 6 sigma. So what you do is this is the specification limit, and you might set maybe an admin limit. So if it's above your administrative limit, you say, all right, redo it. Oh, no. If it's above your administrative limit, you're good. All right, definitely cocaine, charge this, write it up. But if it's between your administrative limit and your lower specification limit, reanalyze. So that you're wasting money, you're wasting time, but you're being more sure, okay? You're not reanalyzing every one, but you set an administrative limit, and then you reanalyze. Now, the forensic chemist could have an administrative limit at 12. And so only in that real narrow gray area would they have to reanalyze. But it's based on sigmas. So the trainee, 4 of those sigmas would push us way up to, probably to 20. And now they're reanalyzing their data all the time, because they get more hits inside 20 and 10. And so your standard deviation is super important in setting these things of administrative limits and rework. And so the better you lock your process down, the narrower the uncertainty, the better you can operate, the more efficient you can operate, and the more confident you can be. So that's a little bit of what we call 6 sigma quality control. So this 6 sigma business. 6 sigma. I'm not sure if it's worked its way into the forensics area. It's from my background in manufacturing and lean manufacturing, but it is a really robust quality program. So if you do get that lab job and so on, and they're saying, well, we've got a training budget, ask to go to 6 sigma training, because it's applied statistics. It will make you better at your job. It will help you streamline the lab, and it'll show initiative to your boss. And if they have the training money to send you to 6 sigma training, absolutely go, because it's great. And it would be a great feather in your cap too if your job is something that you would like to consider doing something different or something else. Having that training would be a really big thing, would open doors for you. Here's just some other data, but I'd like to, well, I'll just show you. This was a cleaning study that we did in my lab. The water drop up here on the upper left is on a clean surface. So a metal oxide surface is polar, water's polar, so they like each other. And so you put a DI water drop on a clean surface, and it spreads out. Okay. So the water drop is a way to measure how clean the surface is. So we took some silicone grease, like vacuum grease, smeared it on the aluminum surface, put a drop on it, and that's what happened. Okay. And then we measured 24 images of these water drops, and we got the contact angle. So the contact angle is this angle inside the drop right here. Theta. Okay. And it's coming in at well, this says 60 degrees. So I think that's this first one here, 60 degrees. Even though that looks smaller than 60. Yeah. And then we got it dirty, and it became this drop here, this this drop on the grease. Okay, so the gross contamination, we smeared it with grease, and then the average came in at 103, and that was that big one that I showed. And a slightly negative skew. Okay, and so then with the paper towel, we wiped all that grease off, and it was completely clean. We felt with our fingers, no greasy feel, and we cleaned it, and we measured the contact angle, and it wasn't any different. What happened was we just made the surface more uniform, right? But the grease was still there, so that was kind of neat. We put the water drop on there, still was 100-degree contact angle. And so then we stick it in the ultrasonic tank, and even got below 60. So it was cleaner than it was at the beginning. So we had what we thought was a clean coupon, softened up the grease, measured the contact angle. The water beat it up, which gave us a wide contact angle. Wiped it all off, and people would look at it and go, yeah, that's dry, that's clean, there's no oil on it. Plenty of oil, totally oily surface. Then we ultrasonicated and pulled all that oil out. Got to 48. Now, Pantex wanted us to get it below 40. Okay, so they said that we in Amarillo they could get to like 35 or even in the 20s, the high 20s. We never got below 40. Okay, and in fact, if we measured it and waited 30 minutes and we measured it again, it was 50. We measured it again after 30 minutes, it was 60 again. What's going on in Huntsville that's not happening in Amarillo? The pine trees. So the oils and the organic molecules that are just spewing out of all these pine trees are landing on all the metal surfaces and sticking. So as soon as they, like you see molecules bouncing off molecules, well, they hit energetic surfaces and they don't bounce off. Those molecules hit that surface and stay. And then we're able to measure that with a water drop. Like we can measure the pine molecules and also any organic things that are just coming out of us landing on that surface too. So we're a source of contamination. So that was, again, just showing you the mini tab. We've got some time. Let's do a Kahoot.